And thank you for everyone who's joined. My name is Scott Linhart, and today I'll be talking about my project, which is Buffelgrass, a comparison of manually collected environmental variables and GIS spatial data using digital elevation models. Now, Buffelgrass is a native plant to Africa and parts of Asia, and was first introduced as Sonoran Desert as supplemental grazing for cattle in the 1940s. The invasive species is very opportunistic and expands quickly in non-native environments. It can be problematic to native species due to clustering, outcompeting for natural resources like water, and more frequent fire regimes. The fires associated with Buffelgrass creates higher temperatures where native plants can't tolerate. It's both threatening to native plants and also the desert soil. So in general, Buffelgrass can create a non-native grassland if not managed. To mitigate the expansion of Buffelgrass, land management agencies and volunteers have been the driving forces to support the eradication of Buffelgrass. Agencies and volunteer groups like the Sonoran Weed Whackers in the Tucson Mountain Park, they're funded, trained, and coordinated by the Natural Resource Parks and Rec, which is a local government agency. The NRPR has used the mixed methods to eradicate it, and this is by spraying with herbicides and mechanically removing by hand pulling. On this picture on your right, I went back in February with the Sonoran Weed Whackers, and they're definitely a very dedicated and fun group. Along with eradication methods, the NRPR have manually collected and recorded Buffelgrass environmental attributes over the last couple decades to give an idea of the different terrain factors in which these invasive species thrive. The problems that we get is the field data collected by different agencies and volunteer programs are not streamlined or consistent, and the surveys are labor intensive and time consuming. So our question is, can many of these manually collected environmental attributes associated with Buffelgrass treatment be obtained from publicly available digital spatial data? Can an automated workflow be created to process these spatial data? So in this study, the objective is to look at these different DEMs to find the slope and aspect values using ArcPro, GIS Pro software, and then compare those with categorical field data using a Nova Test and RStudio. Additionally, we want to create a riparian reference map also of streams and basin layers to visually demonstrate the type of drainage that are found in the Tucson Mountain Range. And then lastly, we wanted to create a model builder tool used as an automated workflow for slope and aspect analysis, and also create a streamlined network. So this is our study area and data. The Tucson Mountain Range is located in the Sonoran Desert west of Tucson, Arizona. The biotic humidity in which the Tucson Mountains are located is classified as a Sonoran Desert shrub, where saguaros and palo verdes thrive. The elevation of the mountain ranges from 663 to 1,429 meters. A polygon was created using a shapefile covering approximately 57,000 acres that try to incorporate the Buffelgrass that we see. Now, the field data was provided by the NRPR and collected from the years of 2001 to 2019. The three environmental attributes we looked at in the study was slope, aspect, and riparian. The slope category data included flat, gentle, moderate, and steep. The aspect categorical data included south, southeast, southwest, north, northwest, west, and east. And the riparian category data included temporary water. To perform our analysis in our GIS software, we downloaded a 1 meter, 10 meter, and 30 meter digital elevation model from the United States Geological Survey. So this is our outline for the rest of this presentation. I will go through the methods, which we will go through the model builder tool that we created. From there, we created the stream network map, a slope analysis map, an aspect analysis map, and then our GIS data preparation. So we can use those to get our results as an ANOVA statistical test for slope and aspect. And then at the end, our conclusion. Here is our model builder. The model builder is an effective way to automate the GIS workflow. Instead of running each tool separately, the user can perform a variety of analysis all at once. To create a stream network for drainage systems, we use the flow direction to determine the direction of flow of each cell using the D8 method. Flow accumulation tool to calculate the accumulation flow of each downslope cell, and then the con tool to create the streamlined rasters. We also created a basin drainage system through using the basin tool. And then the next step was to create a model builder tool to conduct a slope and aspect analysis raster map, in which we use later to create our GIS data values. So here's our riparian reference map. The environmental attribute for riparian had temporary water as the categorical data. So we wanted to create a stream network and basin reference map to showcase the riparian area in the Tucson Mountain Range by displaying these drainage flow. The streams were symbolized by grade type to demonstrate the size of drainage throughout the mountain range. And the streams were categorized as small, medium, and large based on the grade types. From there, we created a slope analysis map. We used a 10-meter DEM resolution for this map. The way slope analysis worked is that it calculates the maximum rate of change in values for one cell to its neighbors. We used the planar method, which calculated the slopes using a 2D projection. And then the output values were measured in degrees ranging from 0 degrees to 90 degrees. Next, we had this clip that shows all three DEMs scaled at 1 to 1,000. Visually, you can notice the difference in resolutions between all three of these DEMs. The 1-meter DEM has definitely a higher resolution than the 30-meter DEM, which has the lowest. And it would be interesting with the Buffelgrass points, if on 130 DEM, if that data point would have the same as maybe a 1 meter. So we'll look into that later on. The next map that we created was an aspect analysis map. Now the aspect analysis map was created also with a 10-meter DEM resolution. The way aspect analysis works is based on the downslope direction of the maximum rate of change in values for each cell to its neighbors. So the compass direction that the surface faces at that location is represented in degrees ranging from 0 degrees to 360 degrees. Again, here is now the same type of comparison of DEM resolutions using aspect cells on a larger scale. It also shows the 1-meter aspect DEM as a higher resolution compared to the coarser resolutions of the other two. Even though the 1-meter DEM has a higher resolution, the question is, will it show the most significance when compared with the categorical data in our statistical test? The next step was to join the Buffelgrass tables with the sample slope and aspect tools. We then used the sample tool to find where the Buffelgrass points overlay the slope and aspect values for all three DEMs. We exported these as CSV files so we could use it for later statistical testing. So RStudio was the statistical software used to perform these comparison tests. It's an open source statistical software where a user can conduct a variety of statistical tests, including our analysis variance test. An ANOVA statistical test was used because we wanted to see if the categorical means of all the groups under consideration are equal or if there is variance among the groups. So after setting up the ANOVA test in RStudio, we got the following slope results. The study wanted to test the effect of different slope categories based on the slope analysis performed in the ArcGIS software. So we used the ANOVA test to find out if there's a different slope values between the 4 categorical groups. When looking at this box plot, a significant variation would demonstrate a difference in the mean values for each categorical group associated with the values in degrees. where the mean values between, let's say, flat, the gentle, the moderate, and the steep would show a p-value less than 0.05. Visually, this means the slope categories would have flat as 0 degrees, gentle would be higher, and so on until you got to the steep category, which would have the highest value in degrees. Overall, all three DEMs showed significant variations with a p-value less than 0.05 between each categorical group. So next step was to set up the ANOVA test for the aspect results. Similar to the slope ANOVA test, we wanted to test the effect of different aspect categories based on the aspect analysis performed in the GIS software. We performed the statistical test to fill out if there's a difference in aspect values between the 7 categories. When looking at this box plot, a significant variation would demonstrate a different mean value for each category group also, with the values in the aspect degrees, where the mean values between, let's say, south, southwest, southeast, north, northeast, east, and west would show a p-value less than 0.05. Visually, the mean of this aspect categorical group would have less or have value degrees where north would be around 0 or 360 degrees, east around 90 degrees, south around 180 degrees, and west around 270 degrees. Overall, 10 meters and 30-meter DEMs showed significant variations with p-values less than 0 or 0.05 between each categorical group, while the 1-meter DEM showed no variance whatsoever. So in conclusion, we wanted to see if slope and aspect values created by using GIS analytical tools were comparable to the environmental attributes collected in the field. In this study, we found that GIS slope values were attributed to the categorical slope data for all 3 DEMs, while the GIS aspect values were attributed to categorical aspect values for 10-meter and the 30-meter DEMs. Also, the model builder we use is a very useful automated tool that can create stream and basin layers and also perform slope and aspect analysis. DEM resolution data functionality and processing time should be factors that are accounted when choosing the appropriate DEMs. The 1-meter DEM functionality was problematic when performing these analyses. There was many times where I spent weekends just waiting for one analysis, and most of the time that would freeze up. So definitely take that into consideration. Lastly, through this study, it shows that GIS data can be used to perform environmental variable analysis and reduce the need for labor-intensive field data collection. Questions?